All right, welcome to the stream, everyone. No, so that is only like a placeholder, something that's moving on the screen while I'm setting things up. Just so it isn't a static screen. So anyway, I'm gonna start off by playing some audio. So prepare for some glitchless audio. All right, so that's quite the improvement since last stream, right? I'm really happy with the results. It seems that the DMA solution that I ended up with works out really well. So it's basically what the code is basically the same as in the last stream, just that I blocked the data cache from being enabled on the memory that I'm using as a source buffer for the audio. So that was kind of an annoying bug, but yeah, it seems to work. So I'm really happy about that. So today we will be merging the Game Boy integration from stacksmashing. I haven't personally worked on that, so it will be interesting to see how that's done. And I honestly don't have prepared any ROMs as well, but I think something that would be cool would be to try out and running LSDJ. So I'm not sure about the license, to be honest. You can download the ROM, um, which I will be doing. So I guess it's the stable. That is the one that I'm going to be using, I guess. I'm just going to download that. All right. So how are the pause buttons working on the NES emulator? Is it mapped to time game select buttons? Yeah, that is correct. Yeah. All right. So in case you don't know, the repository where I'm working is over here at GitHub. So this repository it contains the project structure for the STM32 project, and it contains the project file that you need. That is basically a configuration for the STM32Cube MX software in order to generate the HAL files and so on. And then all the code that is specific for the Game & Watch is here. And then the actual emulator and the actual the actual emulators, they come from another project called RetroGo, which I have forked in order to do some small modifications. So just to go to this source repository here, RetroGo lives over here and is a port. It's multiple ports of emulators for the ESP32 microcontroller. And the nice thing is that it's already been done. So all the sort of microcontroller specific things where, it has been proven to run on a microcontroller, which is really nice. Because otherwise, I would have to take like a desktop, an emulator that's meant to be used for a desktop computer and sort of make that work on a microcontroller. But here, that has already been done for us. So this code base is nice in that regard. But I had to do some slight modifications in order for it to build. And so I created a branch on my fork with some, I guess quite ugly hacks, but it is needed because of header files and so on. And I added some porting layer and so on. So in any case, today we will be focusing on the Game Boy emulator. And as I said before, I haven't actually touched this much. I started attempting a port, but stacksmashing was, yeah, he finished it up really quickly in parallel while I was looking at the NES stuff. So what I'm gonna do today is to merge his stuff into my repository and try to understand what he did and improve the sound perhaps, because now we have a sound solution for the NES emulator. So yeah, that's what we're gonna do today. All right. So I'm just gonna do some stuff off screen here for a little while. Just a second. So yeah, and also I should definitely talk a little bit about this. So yesterday, stacksmashing uploaded a video to YouTube explaining how you can back up your internal flash. So this is basically the hack, so to say. And here there are a couple of scripts that will walk you through everything you need to do in order to back up the external and internal flash. There will be a video about this, I guess, explaining in detail how it works, but I can just explain a little bit quickly how it works. So what it does is that, yeah, first of all, we just check that you have the tools needed. And unfortunately, I think we need to improve a little bit on this because OpenOCD turns out that, yeah, the released version in Ubuntu is too old. You need a newer one. So I was thinking about making a PPA, a pre-built version for Ubuntu. Because if you just apt-get install this one, it will be too old and it won't work, unfortunately. But anyway, we check for some tools. And then we, let's see here. Yeah, we will upload some code that will dump the encrypted flash to RAM. We can look at that code too. Can open that in a different tab so I don't have to jump around. That one, I think. Yeah. So what this, all right, flash. So what this does, it dumps the RAM, and then it loads the flash dumper. So flash dumper is another project, which will, let me show you that as well. So as you can imagine, I haven't really prepared anything of this. This is just 100% ad hoc. So flash dumper is a piece of code that will initialize the flash driver. Let's see here. Yeah, here we go. So it will initialize the flash in a specific configuration, and then it will read all of the flash at address 0 into the RAM at OX24, which is 1 megabyte large, and the flash is also 1 megabyte large. So this is very convenient. So when it's done with that, it will just set a flag and loop. So what we can do then is that we can, okay, here it's just waiting. Yeah, so that also works. But you could essentially loop and wait here until this flag is done, and then continue the script, but sleeping will work because this is sort of deterministic in the time. There is no real uncertainties. So anyway, when this code has been executed, it will have initialized the flash driver, and then it will have dumped all of the flash unencrypted, or I mean encrypted, just the way it is stored on the flash in raw. So this is like equivalent to using an external flash reader. And then it will store that in RAM. Yep. And then we will dump from RAM into this file. So that is what this part is doing. Let me see if I have anything on the chat. No. Okay. So now we have the flash backed up in its raw mode, and then we will check some checksums of a part of the RAM, and then also of the part of the flash. Yeah, exactly. And when that is done, we know that yes, we have a good dump of the flash, which means that if we change the flash, we can also revert it and go back. And that's kind of important when you're messing around with other people's devices, that you know that you have a good backup. And then it's time for the really interesting part, which is to back up the internal flash. So as you might know, the STM32 on the Nintendo Game & Watch is locked in this so-called RDP1 level, readout protection 1, which means that you cannot, when debugging, read the internal flash, but you can read and execute RAM. And that's what we're using here. So we found a way to upload code to the external flash that is then being loaded and executed by the microcontroller. And so we wrote a piece of code over here in the payload. So this is essentially the so-called exploit, if you want. But it's basically a big NOP sled. A NOP sled means that every instruction here is a no operation opcode, which means that if you don't know exactly where you will be executing from, you can put a lot of NOPs in order to have a safe start to execute from. So for example, if your code is being executed from this part or from this part, it doesn't matter. But if this is your code and you start executing from here, which you want, or you start executing from here, that is a huge difference. So that is why you have a so-called NOP sled, and that's what we're doing here. So we have this NOP sled, and then we have a very naive memcopy implementation here, where we have two registers which contain a 0 and a 4. 0 means so we will be using R2 as the source address and R4 as the increment. And then here in the R0, we load the source address, which is over here. So this is the internal flash. So the pointer to the internal flash is loaded into R0. And then the destination, which is where we want to copy to, is stored in R1. Then in every iteration we do this. So we will add R2 to R0, and R2 is 0 from the beginning, and it will be incremented. And then R1 will be incremented with the same. So R0 is the source, and R1 is the destination. So essentially we're taking these values, these pointers, and incrementing them. That's what we're doing here. And then we will load. The square brackets mean from the address, so it's like a pointer to reference. So we'll take the R0, which will be this, plus increment, and we will read one word from that place. And then we will store that in the register R3. And as you can see, we haven't used R3 before, so this is just the temp variable. And then we will store the contents of the register R3 to the address where R1 is pointing to. And R1, as you see here, is the destination, which is this, plus increment, which is done here. So essentially, we will take one word from this, plus increment, and store it in there, plus increment. And then we do the actual increment here. We take the R2 equals R2 plus R4. So this one plus equals this one. And we loop and loop and loop and loop and loop until it crashes. Because when it crashes, it will end up in something called hard fault handler, which is sort of a crash handler. That's good because it will get stuck there. And when it gets stuck there, we will have the full flash memory in RAM. So that is how that works. If you have any questions, just say so immediately. I will try to catch up or keep up with the chat. I have it on the screen here, but yeah. Let's see here. Yeah. All right. So that is how that part works. So essentially, now we have reached. Let's see here. Right. So at this stage, we are using. Let's see here. Actually, I haven't read the script before, so this is sort of a first for me too. So here we are creating an XOR key, I think. Yeah. Right. So we are taking the payload that we just looked at, the NOP/SLED and memcopy, and we are patching the backup flash using information from the ITCM backup and storing that new patched flash in this image. So this file will contain exactly the same as the original flash, but it will also include the payload, encrypted using the RAM backup. All right. So now we have a new flash image. We need to put that onto the device. So the way we do that is that we use the flash loader, which is another little project that I can show you. So this was flash dumper that we looked at. So flash loader is essentially the same. It's just slightly different. It will write to the flash instead. So the way this works is that it again initializes the flash, and then here we enable writes to the flash. So this sends a command to the flash, and then here we tell the flash to erase itself, because flash memory works like this, that you need to erase it in order to write to it. You can only transition from a 1 to a 0. You can never go from a 0 to a 1. You need to do an erase of that page. So this is kind of simple. We just tell the chip to erase all of the chip. Everything is gone. And then we program the contents of the RAM into an address of the flash. And that's it. So this flash loader script, it will copy the new flash image into RAM, and then it will do some scripting to make sure it's smooth, because we have a few flags that we check and so on. It's kind of convenient to use. All right, so when this part is done, that is sort of a critical part, because it takes quite a while, because we need to upload the whole RAM, or the whole flash into RAM, which takes a while with the SD links. And then the actual flash operation is executed, which also takes a while, like 10 seconds at least. But when that is done, that means that we now have the internal flash memory in RAM, and that can be extracted. So that's what we're doing here. So now we're dumping from the OX2400 area, and we take 128 kilobytes, and we store that. And when this is done, we check the checksum of that. And it turns out that every single unit is the same. So we can have a checksum, and it will verify that the dump was actually good. Yeah, it uses flash backup plus item backup to generate exostream and generates a new flash image. Yeah, exactly. Okay, so that was part 3. And then part 4, this is sort of the most dangerous part of everything, because if you have failed to backup, performing this step will wipe the device, and you will not be able to come back. So that is why you need to run the scripts in sequential order and not skip a step, and be sure that, yes, you know what you're doing. So this performs something called that we are changing RDP level from 1 to 0. And the way this works is that inside of the STM32, it will allow this, but it will erase all of the flash in order to transition from 1 to 0. But the thing is, since we do have the backup, this doesn't matter to us. This is fine. So we do this, and this can also be a little bit, sometimes it doesn't work the first time and so on. Just power cycle the device and try again. Eventually it will work. And when you are done, you will have a completely empty device. So you have to restore it. And so what this script does is that it will upload the internal flash backup and the external flash backup using the various scripts that we have already talked about. So it will use the flash loader to program the external flash. And when this is done, you can now enjoy your Nintendo Game & Watch in an unlocked mode. So that is how that works. So it didn't take that long to explain, but I really thought it was important to explain a little bit, because I guess someone might be a bit confused about how it works. So anyway, now we are done with that. We can go back to the Game & Watch or Game Boy stuff. Okay, there's a question. Let's see here. Well, the exploit is trivial, and it was obvious as soon as you mentioned that some code is executed from Flash. More interesting is how this piece was found. Yeah, I mean, you're right. And for the initialized people, yes, it will be trivial. When you hear, oh, code execution, okay, now you know exactly what you need to do. But I still wanted to explain it so everyone understands. All right. Thanks. Okay, so how this piece was found. Yeah, well, I mean, Stacksmashing and we were discussing back and forth, theorizing about various things related to the hardware, crypto, and I don't know really. We were just exploring things the way you do, just like a CTF. Ah, yeah. Yeah. Yeah, I think one realization was that we were dumping the RAM and loading it into Ghidra, and turns out that you could actually it was actually code that was loaded into RAM. Yeah. Yeah. And I think if you look at the timestamps, from that point until I sent or until I actually managed to dump the internal flash, it wasn't that long. It was so funny because once you get going, it's so hard to stop. So cool that you guys are describing the entire process in such depth. I'm planning on getting a unit so I can follow everything from beginning to end on my own after Christmas. Yeah, that's awesome. And please let us know how it goes. And if you get stuck, yeah, let us know. So I think I added a bot to this stream thing, but it doesn't seem to work. So I'm just gonna do this and say welcome to the Discord. Join it and feel free to discuss. So I added a timer, but it doesn't seem to work. Anyway, yeah. So that is how it works. All right. So I'm just gonna prepare some stuff here. Let's see here. Right, 6. Okay, and there, there, the timer actually expired. Okay, perfect timing. Just about yesterday, I found that the author of Cordless was banned on Discord. I don't know who that is, and I haven't followed on that story. Oh no, I just realized that I forgot to record the stream, so that was kind of stupid. I started recording now anyway. Damn. All right. So again, sorry for being a little bit. I'm gonna be a little bit quiet for a while because I need to prepare some stuff. But I can change the camera and just play some stuff here. Um, oh, thanks. That's actually really nice of you. If you don't mind, we can talk offline later on and see if we can merge. Well, that only works once, right? You cannot rickroll twice. Thanks a lot, GTH. All right, I guess this is going to be a little bit boring because I will have to merge between two repositories and a few files have been renamed and so on. But Yeah, let's just get to it. Okay. Yeah. So the makefile is stupid. I wanted to fix this, but essentially the way this makefile works is that it takes the file name of each file you want to compile and creates an object file in the same directory. So if you have like source lcd.c and then you have like a file called lcd.c over here, it will overwrite or it will conflict, and that is really no fun. So yeah. Okay, so let's do that with the LCD as well. All right. So I guess these are right. Wonder why I changed it. Oh yeah, because of the indexed color. So yeah, we should keep it indexed. So before we started to diverge, we used the RGB 565 frame buffer, but now I use a LUT8 frame buffer. So we have it's a lookup table, and so that's changed. So yeah, let's do like this. Okay, so I'm sorry I can't really share the screen to the left of me, but it's basically I'm looking at the other project. I'm just going through the files we need to merge. But it's not super fun to look at anyway. But you will, yeah, in a few minutes I will have something to share, I hope. Let's see here, source, and then I guess, yeah. Ah, there we go. Make was made exactly for that task of not having to go through each file when build scripts. Well, I haven't spent time to fix this makefile. It is so this is a generated makefile by the STM32Cube MX project, and the way it works is so the issue is basically where is it? This part, because it matches on each C file, no matter. I guess it's this part where it will strip out. It will generate an object name. Yeah, it will just put the objects in the same build directory. So I mean, this makefile is not so nice. But to be honest, uh, it's not much work to do it. It's just work that we haven't spent, because you need to prioritize what you want to work on. Otherwise, you end up just spending days on making stuff nice. But I want to move forward as well, so it always takes some time. But sure, I mean, if someone is up for it, yeah, please rewrite our makefiles and make them nice. Why not? All right, let's move on. So that was input. making stuff nice usually turns out to be yeah, definitely. And that is why we haven't done that. So in order to get to the goal as fast as possible, to have a proof of concept showing stuff on the screen and so on, we have just, head first, run fast. That's why it is like it is. Okay, make file. Oops. Actually, I just found out there is a diff tool built in Visual Studio Code, which is kind of nice. So you can do like this and do like that, and then you can diff two files. Really nice. I guess I actually want a debug build. Right, and this will have to be modified as well. All right, that doesn't belong there. Right, so what this does, it tells the build system to depend on the makefile. So whenever you change the makefile, you will rebuild the whole project. So let's change that, because I did that on this side already. Yeah, I mean, in a nice world, you would spend time to have one common makefile and just change a few things, but we will get there, but not today. Oh yeah, this is also kind of my old ugly hack. We don't need this anymore. So this was in order to flash the external flash with the Glasgow programmer, but we don't need that anymore. So now the makefile has been fixed. Very nice. And I guess I can copy. Let's see. This one and call it like that. So I haven't really checked how the ROMs are stored. Let me just check that. Right, so it's very similar. So let's do that like that. I think that is still valid. Yep, it is. But this one, on the other hand, is probably not needed. But that can be improved. So I think, yeah, maybe the ROM is not being loaded into RAM. I haven't checked the code yet, but we'll be getting there. So let's see if anything changed with the linker script. Oh. And we can do, oops, like this. And we can see easily what's changed. So on the right side, we have the Game Boy stuff. All right, it's essentially the same, but for some reason this one is not there. Did I actually use that? No. Okay, I guess it can be removed. And then oh right, that is the thing. I wonder if this is not more correct. Linker scripts, they are horrible. I will probably never learn them fully. But essentially, what all of this does, it tells the linker where to actually put stuff. And when it updates the symbols where stuff is located, and when you reference to different things, it will resolve and put stuff in the various places and update the pointers. And what this piece does is that it stores the code or data or whatever in the flash, but the pointers will point into RAM. But then in the program code, we need to actually copy the stuff from the flash into RAM. And in order to get the correct pointers, we need to do stuff like this. So what this means is it creates a symbol called RAM start, and the value, or it will be located in this current position. And the same thing with the RAM end and so on. And then we can use that in main.c and over here, where we actually copy stuff from RAM into, or sorry, from flash into RAM, and then we can execute and so on from RAM. Okay, cool. So I guess I can actually merge these so they are. I think honestly they can be identical. Oh right, the audio stuff is moved to HP RAM 3. So this is actually important. Yeah, I forgot about this. So what I did after the stream was to create. So actually, the microcontroller has an extra memory region that we didn't map before. So at this address, we have 128K of even more RAM, and I configured the MPU, the memory protection unit. I can show that. And STM32CubeMX. Just 1 second. And we go there. I haven't migrated the project file yet. I will do that. So the reason why I got that pop-up is because I'm using a newer version of the tool. Anyway, so if we go into, I guess it's system, Cortex. Yeah, so this part, basically, all of this is part of the MPU. So that's memory protection unit. And I've configured it to be as permissive as possible. So a memory protection unit can be used to block access to a certain memory and block certain types of access. For example, you can execute but you cannot read. You can read but cannot write and stuff like that. And then you have multiple levels of access. So if you are familiar with how a kernel works, you have sort of a kernel and user space-ish in a very, very simple way. So you can have like a so-called kernel having full access and then a so-called user space which cannot do everything. Anyway, I've just configured one region, but now for some reason it doesn't show up here. No, right, it's region 0, right? So it's indexed at 0. So we can support up to 16 different settings, 16 different region settings, and I've only configured the region 0. And what I did here is that I told it to operate on the OX3 and a bunch of zeros, so it's this memory area. And the size is 128K, so that also matches what we have here. And I say all access permitted. You're fine to do anything here, no blocks whatsoever, but the data cache and all of the caches are disabled, which means that the memory will not be cached. Because it turns out that the DMA is really, really sort of sensitive for caching. Like you can get it to work using some other hints that you can tell the MCU, like you can hint certain areas of memory to be flushed from the cache and so on, but this way it will not even be cached, so it will not even consume cache memory, because the cache is, I think, 4 kilobytes on this, 4 kilobytes of instruction and 4 kilobytes of data cache. So anyway, by doing this, we have essentially told the system to not cache any memory on this area. And that way, when I do DMA, it will just work. I don't need to do any special stuff. Is the source available on GitHub? Yes. Thanks for the link. Perfect. Correct. So again, going back to the code, honestly think we should keep it this way, like so. So basically these are identical, but I still want to keep them separate because we might need to do some hacks and so on. So let's just keep them like that. And Yes. Okay. So let me just see if it still builds for NES. Right. GW Flash. So I need to wait a minute. Did I forget to copy files? Yeah. Okay. Let's rename. Were you able to force proper screen ratio yet? So now the way we're doing it now is that we are using the native NES resolution and just adding black bars, as you can see on the video that I should be showing right now. Can do like this. All right, this. It looks pretty good like this because there is nothing on the edges. But let me load. Yeah, that's how it looks. Oh no, we have a spammer. Kick it. Can I kick it? So I blocked the user, but I'm not able to remove the message. Well, I blocked them at least. Okay. What is proper? Yeah, JTH, I think you you probably know this the best. Yeah, exactly. So I guess, yeah. So our resolution is this, three, or yeah, exactly, 320 by 240, and 256 by 224 is completely different. 256 by 240 is also completely different. But we want to map it to this as much as possible. And as you know, the original firmware, the Nintendo stock firmware, has some sort of scaling going on. Or not scaling, but what's it called again? Yeah, they seem to fix the aspect ratio somehow. I don't know if they render a little bit more. We can actually take a look at that. So if we go to this one and we run the restore script, let's see if it works. All right, I'm not actually sharing my console, but yeah. So what I'm doing now is I'm restoring the stock firmware. So let's take a look at how that looks. It's restoring, it's working, and here we go. So now the flash loader is executing. So we're waiting for the execution to finish. Yeah, okay, it's done. And all right, I have to press a button. Oh, it failed. Okay, so if this happens, if you see this, that means that the external flash did not manage to get restored, and that there are lots of reasons for this. Basically, electronics are weird, so sometimes it just doesn't work. So let's try again. Okay, sometimes actually the programmer can have some issues. There could be electrical issues. What's the name of the Game Boy emulator you will be porting? Okay, so let's check that out. So it comes from the RetroGo project. So the RetroGo project is again a collection of emulators. Which I forked in order to make some patches. So it claims to have support for Game Boy, Game Boy Color, Sega Master Systems, Sega Game Gear, and all of the good stuff. So I guess it's the GNU Boy, and GNU Boy has been copied into this repository, so I guess we have to Google it. So is this the actual source repository? Perhaps. Yeah, I suppose this is where it comes from. Or yeah, okay, maybe even here. 2003. Yeah, taken from the official page. Is there a link to the official page? No. I guess the original page might be defunct because it's so old. But it's GPL, so that's nice. We can use it. So I guess somebody imported it. I honestly don't know. There are a few patches here, it seems. Yeah, okay, so that is the official release. Yeah, that's kind of interesting because I don't know who the author is. Like, I haven't checked, but here are a bunch of fixes, so that's kind of nice. Anyway, let's get back to what we were doing. So okay, I guess it's the demo monster that is playing a prank on me right now. I'm having issues with the backup, so I'm just not gonna do it. Okay, so let's go back to our Nintendo stuff. Right, so I'm gonna update. Yeah, that's gonna work. Okay, I'm having some issues. Right, so the LCD driver needs to be renamed. Let's do that. Okay, something broke. Nice. Okay, so it seems to build. Let's see if it still works. So I just want to have like a good baseline so that I know that NES is still working before attempting to continue on the Game Boy stuff. Yeah, okay, so it's flashing the external memory. And it's done. So now we're flashing the internal memory. And yeah, it seems to work. Good, we have a good baseline. Perfect. So I guess something is a little bit wonky with the scripts for restoring. Shouldn't really be a problem, but for some reason it is. All right, just a second. Thanks. I will download that if I find the link. Yeah, there we go. Copy link address. Okay, so I'm gonna do like that. And of course. Cool. Feel free to. Yeah. Okay. Cool. All right. Gonna need to do like that. Yes. Okay. Right. Back in business. So I guess we're gonna run the script, update GB-ROM, and see if it. Let's just double check so I don't do anything stupid here. Oh, okay, it's already here. It was stupid. Yep. Just gonna double check the name. Yeah, should be fine. Bam. So now we have a Flappy Boy somewhere. Yep, perfect. And the length is 32K. Oh, this is good. It's a small one. Perfect. So let's build. Okay, so let's clean up the build. So this is like this. Yep. Let's try again. Okay, I'm getting some. Okay, okay. I see what's wrong. Yeah, I was gonna restore it in order to see what's going on with that, but yeah, let's do that later. I'm gonna focus on Game Boy now. Okay, so the reason why it's not building is because I'm not using the correct submodule. So let's try to fix that. So I'm going here, and then I know that there is a branch. So I'm guessing, let me check actually. Okay, so this commit contains the patches we need. So I'm standing in this branch, git merge squash. Hey Miko, nice to see you here on the stream. I might have some MAME questions for you later on, but not right now. I guess at some point we should try to port the actual Game & Watch emulators from the main project. And if I don't remember incorrectly, you have quite some experience with that, right? I mean, MAME in general, at least. All right, let's see what happened here. It is stretched. Oh, I didn't know that. That's interesting. Okay. All right. I mean, we could also stretch it. That's no problem. And I guess if we use that nice 1.5 times stretching algorithm, it might actually look, I guess, decent. Yeah, so, yeah, exactly. We could try that 1.5 stretcher. So I guess 240 times 1.5, 360. No, that doesn't. Actually, it's this one. I wonder how they do the scaling. Because it doesn't. I mean, we have the 320 by 4, 240, right? And if the original one is, I don't know. Yeah, I agree with JTH. Like, I love crystal clear pixels. Like, if you can scale with a factor of 2 or 4, that's nice. Once you start to go with the fractions, it might not look that nice. But sure, let's keep it an option, and then people can do whatever they want to do. Let's get back into conflict merging. That's tough. If you haven't coded that much, conflicts are the most fun part of the job. Actually, it's what I love to do. Not really. And also, this is extremely frustrating. Like, you look at this and you think accept incoming change. Okay, that probably means that I want to use what I'm importing. But no, it's actually the opposite way. Or not? Come on. I want... Let's just take both changes. Whatever. Okay, we added a comment. I can just remove that later. Okay, what happened here? Okay, it's basically the same. I'm just gonna take both changes. Then we can clean it up later. Alright, need to save. So it's a little bit unintuitive with Visual Studio Code when you do conflict resolutions. Like, first you click, but you still have to save the file, and then you can press the plus. But I guess it makes sense, but yeah. Here are some comments, very nice. Yeah, let's take them. Oh, there are multiple conflicts. Yeah. So whenever I get frustrated with conflicts, I just take both changes and then I look them through in a second sort of pass, because it's always messy. So now we have the changes. I'm gonna unstage them so that we can change them and clean it up. So we can clean that up. Yeah, we don't want that. I think. Okay. Why is it that no IDE seems to be able to make it clear? Yeah. Yeah. I've given up at this point. I just there is actually one tool that I like, which is called Perforce Merge, because at some point in my life I was forced to use the tool called Perforce, and if you don't know what that is, bless you. But the merge tool was pretty nice. It should be possible to do a non-integer scale and then apply horizontal filtering to get rid of the shimmering like they do on the Mini NT and Super NT. Thanks. If you know of an algorithm that I can look up or something, please post it, and I will be sure to look it up, because this stuff is very very interesting, and I haven't actually done any graphics programming in like 5+ years. So thanks. Just post the links and write algorithm names and stuff. Just fill the chat with the good information. I can look it through later. Nice. I like these comments. So right. So this is for saving and loading the RAM state. So essentially what we want to do is to store this on flash at some point. Not right now, but eventually. Okay, and here we rip out that. They may employ a bunch of hacks to make it work and look nice. Yeah, for sure, definitely. And if you can figure out what kind of hacks they do, I think that would be cool. Because honestly, the stock emulator looks pretty nice. I think it looks pretty good. We're aiming for a universal solution. Yeah, I mean, for sure, definitely. So it would be nice to have sort of a base emulator project, and then you can just include any emulator and apply any kind of filtering and so on. And then we can share that filtering across the emulators, so you don't have like 15 different implementation of the same thing. Good morning, Digister. Nice to see you here. All right, this looks good. Okay, so here is some sort of lookup table. Okay. But this is the shared lookup table. Okay, okay. Sounds like an amazing goal. Did we get full support done for the... yeah. Yes, actually, yes, we did. So I can show you in the... Actually, I guess I have the code here. So in the Flash driver, you can select SPI mode, quad mode, and you can select vendor, MX and ISSI, which is the one we implemented in the previous stream. And this driver actually works, so it isn't just an API. And then in the Flash loader, let me just pull that up here somewhere. Yeah, so I refactored it a little bit. So the Flash script can now flash. It can program at a specific address, and it can also erase or not erase. So I wrote a different script that will iterate through the image you want to flash, for example, a 16 megabyte image, and it will chunk it up, and it will program each 1 megabyte chunk and only erase the first image or the first chunk. And I verified this, and it works with different sizes. Like if you're a little bit larger or a little bit smaller than a perfect 1 megabyte boundary. So I'm pretty confident in this. It worked, at least for me when I tested it. So yeah. The only big drawback is that it takes like 30 seconds per 1 megabyte chunk. So once we start to need that all of that memory, I think it would be extremely nice to spend some time on the allocation of the external flash. So for example, keep the first page or the first X amount of chunks or pages as untouched, so that you can have storage in some section, and then you can have program code that you change many times in a different region. And that way you don't move stuff around all the time, and you don't need to reflash like the whole flash. So for example, the emulator, so let me just scroll up here a bit, I guess. Yeah, so this print, it shows the size of the various memories, like how many bytes we're using in each memory. So for the external flash, I'm using 730 kilobytes, which is quite a lot. But this includes a ROM as well. So for example, we could say that the first megabyte is only for program code, and then the rest is for storage, and then we can have like a file system, like a very basic file system. And then you can also have persistent storage for the emulator states and save games. And if you're porting like LSDJ, you could have your songs in a whole section there. And whenever you need to program, we only reprogram the first part. got you. That makes sense. So, in approximately how much room for the ROMs on this chip after all other code? I mean, Game Boy ROMs seem to be very small, so I honestly think there will be a lot. Yeah, I guess there's a little bit of stream lag. But anyway, I like to explain stuff because when there is a question, there are probably 5 similar questions that were never asked. So please just write in the chat and ask whenever you're wondering something, and because I'm sure someone else will be interested in hearing the answer. So just keep asking. So going back to the merge. So this is the shared render file across Nintendo and Game Boy. So I'm trying to remember how I did this port. um, oh yeah, they are over there. So because not all of these changes might be included, like maybe we don't need all of them, but this definitely shouldn't be there. I guess maybe I didn't need that. How about, wait, this is for SMS Plus. Oh, right. I really don't need this because that is for the Sega stuff, which we haven't even started looking at. In the last stacksmashing video, he mentioned that it's possible to replace the 1 megabyte memory with 16 megabyte. Can you elaborate on that? Yes, definitely. So, let me show you on the camera. So I built a small adapter here. I guess I can do it like this, which allows me to change the flash. So I soldered some wires on the PCB so I can have an external flash memory. So I can remove that and plug in a different one. So this allowed me to easily iterate and implement support for a larger flash. So I made a different little cartridge with the 128 megabit. So 128 megabit is 16 megabyte. And what this flash is of a different vendor, which takes different commands. So it works a little bit differently. And that is why in the flash driver, we need to have some handling of those different vendors. So we use different commands depending on which vendor and which mode we're using. And yeah, in the last stream, if I don't remember incorrectly, I finished. No, actually, in the first stream that was, yeah. So anyway, it is done, and it does support the big flash. What the big flash, so if you want to use the stock firmware for some reason, you cannot use any flash. So this flash is of the vendor from the vendor ISSI, and if you use the stock firmware with this flash, then they are going to use commands that are incompatible. So if you use a different vendor, you're sort of bound to use Homebrew only. So I'm just going to read the chat. There is a recording on YouTube walking through that. Yeah, that's what I was just asking about. Was support for that done? How was explaining the drivers done? Yeah, very cool. Are more peripheral support possible? To elaborate on that, yes, there are a couple of free pins left. So here is the microcontroller again, with the pin mapping of pins that we have reversed or figured out in some way. Some of these pins, like the SW, these ones are also used. And there might be a few other pins that are used. But yeah, if you want to solder onto the chip, yeah, you can probably use different peripherals. One peripheral that is the most popular one is probably the USB one, and that is unfortunately multiplexed with the LCD driver. I think it's this pin. Yeah, you see here, USB on the go high speed. And unfortunately, this, or actually, this is for the D1. Yeah, but anyway, there are a few other pins here. What this means is that if you want USB to work, you cannot use the LCD at the same time, and also it will be electrically connected to the LCD panel, which may interfere with the signal. So maybe USB doesn't work even if you only use USB and not the LCD in a bootloader, for example. So, but anyway, to cut things short, yeah, there are a few pins left. Maybe you can use different peripherals. But if you want to use, for example, an SD card on the instead of the flash chip, well, I guess it's possible, but you probably cannot use it in the memory mapped mode, which means that you will need to like copy pages manually and so on, which is not impossible. Maybe it will even work out pretty okay, but there is extra work needed. And I haven't looked into that myself. You can build whatever you want with microcontroller. Yeah, definitely. But there are still limitations. For example, yeah, if you want to use like a specific peripheral that is already being used by different pins. This poor view of dangling wires make me want to design alternative backplate and cartridge access. Yeah, definitely. Like that would be really cool. However, I think a lot of people buy this device because of the case, and starting to mod the case is a little bit sad, at least to me. But yeah, for sure, it can be done. Hacking on a Wi-Fi module or control support. Yeah, so I am not personally doing that. We have discussed it a little bit. Oh, sorry, you're not. All right, I can do like this. Yeah. Yeah, to elaborate a little bit, I'm just trying to catch up on the chat. So to elaborate on the Wi-Fi module or controller support, definitely you could design a Wi-Fi or Bluetooth module that is included inside of the module, and then solder that onto the SWD pins, and then in the software you could reuse these as GPIOs, and that way you only need like 2 wires to be soldered onto the microcontroller, and then you have both SWD and GPIOs, 2 GPIOs, and then you need to sort of come up with a bit bank protocol, because I don't think these are these don't have like I2C or SPI or anything like that. So you need to do that yourself. Alternatively, that you use SVD IO, like ARM SVD protocol, to debug the chip and upload stuff that way. Which is the way we do it with this stuff. So I mean that it's definitely not impossible, but I haven't looked at it. And also, I guess we need to keep the cost down because you know it would be a little bit strange to spend like, I don't know, $20 to mod this. I don't know, but there are some really cheap Wi-Fi and Bluetooth modules, especially if you use like ESP32 or something. They have come down in price a lot, so I think that would be pretty cool. Okay, moving on. In theory, since this driver is done, can you swap out the chip on board? Also, can we solder the wires to USB to flash through USB-C? All right, a few things here. Definitely that you can swap out the flash. So I did this solution in order to quickly be able to swap it out and program it using an external programmer. But in the future, I will definitely solder it down. But remember, if you use a chip vendor that is different from the MX vendor, it will not work with the stock firmware. And honestly, I haven't tried a 16 megabyte flash with the stock firmware with where the flash vendor is MX, so I don't know if that will work. Maybe they have some code somewhere that checks information about the chip and refuses to run if it doesn't match. I don't know. I haven't checked, so I cannot confirm that it will work. But anyway, if you only care about homebrew, definitely you can solder it. And then I'm just gonna show a picture in a few seconds about the USB mod. There we go. Yeah, so you can see my screen now, right? So my friend Jens, we made this mod together where we simply took a copper wire, two magnet wires, from the SWD IO and clock, and connect them straight to the data IO and clock. And using this method, you can close up the unit and connect the USB-C. You need to have a USB-C adapter that takes a USB-C connector male and breaks it out. And then here you have the D plus and D minus, and you can connect those to your debugger. But the problem with this mod, there are multiple problems. So first of all is that these wires are tiny. You probably want to expose the reset pin as well, because otherwise, yeah, like if the battery connector is connected and you lock up the processor, you cannot exit that state if you're unlucky. So you probably want to come up with a different solution. And also, I haven't beeped it out, but it could be that you have the SBU pins here. I don't know. Actually, we could actually check that on the picture here. So the way, how many pins do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So USB connector with 12 pins where the two outer pins, this is probably ground. So let's see here. A 12-pin connector. What actually do we get? Yeah, this is probably, it looks like a different one, but it wouldn't surprise me if it's similar to this one. So here they have the ground and VBus and ground and VBus symmetrically. And then you have the D plus, D minus. I have the two sides and the two sides. And then you have SBU1 and SBU2 and the CC pins. Yeah. So they have most likely connected the CC pins to, actually maybe they don't even connect the CC pins, but yeah, this looks like the 5.1 kilo ohm. I haven't measured it, but it wouldn't surprise me if this is the 5.1 kilo ohm resistors that you need to have on the CC pins in order to identify as a USB device for the host, in order for the host to sort of enable the port. But if the SBU pins are accessible here, maybe it's these pins, I don't know, I haven't checked it, but if it is, then you could use those pins to connect to reset and use that. So enough about that sidetrack. But anyway, I think this is a quite promising mod because it's extremely cheap. You only need a wire or two or three, but it's basically free. And then the adapter is not expensive, but it's not really accessible right now. But we could build like a PCB that includes a programmer and that you can connect into the USB port, and then you can just program and load stuff. That would be pretty cool, and I think I might do that. I could make a PCB on the next stream, perhaps. Would be pretty fun. And with a quick JLC PCB manufacturing time, we could have it in like a week, and we can try it out. Would be pretty cool. So moving on in the chat. Can't see the diagram. Oh yeah, sorry for not showing the screen before. It's always possible to use some external chip for USB. Make some motherboard on FlexPCB. Yeah, that is definitely true. That is definitely true. But at the same time, the complexity of this mod is pretty low. But a mod chip, I guess the lowest complexity, like if it should be able to be installed by someone who is not very good at soldering, I guess a flex PCB with a mod chip in this area connected to the debug port only is probably most likely to work out well, because then there's no fine pitch soldering. Having to solder this connector is tricky, even if experienced hardware hackers might say, yeah, it's no problem. You just take it under the microscope and it's 5 seconds and it's done. Yeah, but not everyone has a microscope. So even if it's nice, not everyone can do it. But these, I think people can solder. Okay, moving on. Regarding Wi-Fi, ESP32 are already there and it's trivial to hook them up, but it's still quite a project for an average person. Yeah, but if we make a flex PCB, we could put, and also, right, so this might be important, level shifting. The STM32 operates at 1.8 volts, so if we are going to do I/O with the chip, we probably want to operate at 1.8 volt as well. I want to take a better photo and make a diagram for this. Oh yeah, please do. We probably need to reverse PCB at some point. Yeah. Can we get a shared shopping list with links for these different things and solutions? Yeah, so right as of speaking, this module cannot be bought right now. My friend makes it, but he will release it in a few weeks, perhaps, a few days or weeks. And when it is available, I will post a link for sure. To understand what is possible to use of what's already there. Yeah, exactly, for the PCB reversing. Yeah, definitely. There are a couple of chips on the device that we aren't really sure about. And I just got the Twitter mention from someone who was identifying some chips, which is really awesome. Because some of these chips are really hard to identify. Like they're just black boxes with no markings whatsoever. So, yeah. All right, interesting. Sorry for that. Resistors are probably there because we all need the USB ports to enable full power for charging. Yeah, exactly. So I think the 5.1K is probably there. There are currently only problems, no solutions. Yeah, you're right. That's what we are working on. All right, finally caught up with the chat. That was an interesting tangent. Because modding the PCB has to be done in some way. And we still, I mean, we are in the infancy of modding this thing. Right now we are doing some pretty cool stuff, but there's still so much we could do. But I'm a bit worried about frying something. Wouldn't it be safer to misuse the pins used also for analog audio? Yeah, exactly. So that is what the SBU pins are for. Sideband signals. And usually, if you connect this to like a PC, you don't the SBU pins are not even. Or, no, I shouldn't lie here. It depends on how you connect it. Like if you have a USB A connector, like a USB C to USB A, like if you have this type of connector, this type of cable, then there are no SBU pins. They do not exist. And it would surprise me if the few pins that we have here, if any of those are the high speed, or actually super speed data pins. So USB-C full pin out. Let me just show you what I'm talking about. So USB-C is kind of interesting. You have a lot of signals. So first of all, it's reversible, which means that all of these signals have a counterpart on the other side. Let me just check the chat. Flexible seems the best. Thing is, you'll need a full breakout for USB-C to interface to them. With USB pins, any USB-C to micro USB cable will work. Yeah, again, it depends on how you want to use it. Like how do you want the mod to work? So I was thinking, if the SBU pins are actually available on here that we can solder, then those will probably be the safest pin to use, because if you charge using this type of cable and connect that to a PC, then it will be safe because the pins won't be connected at all, I think. But if you use like a USB-C cable and connect it to a Mac that has Thunderbolt and all that jazz. Then it's gonna start to send PCI Express onto those pins, and sure, the voltage swing is not very high, but it might be bad on the other side, like on the reception side. Maybe fry your PC by sending 3.3 volt into your PCI Express PHY, you know, um, that would probably be a bad idea. So yeah, I honestly don't know. Okay, not worried about this, but rather about any inter-device misunderstanding. Yeah, exactly. Thinking rather of first-gen Raspberry Pi 4. Yeah, okay, so the problem with the Raspberry Pi 4, for those who don't know, is that they didn't connect the CC1 pins correctly, CC1 and CC2. They shared a resistor. So let's see, there's guarantee. Let's see here. Yeah, here it is. Yes, so it's a little bit blurry, but here you have the CC1 and CC2 pin. And the USB-C specification tells you that you need to have one separate resistor for the CC2 down to ground and one other separate resistor from CC1 to ground. But here they share the resistor. Or no, this might be they do something really strange here. There are two resistors, but only one is always connected to ground. Yeah, exactly. So this is the bug. So this is not the correct way to do it. And I think you might be referring to that nickname 77. So the way the issue with this is that here you get some sort of voltage divider, which ends up loading the specific current which identifies as an audio device. So the CC pins can tell the host what kind of device it is. And yeah, and the way it was hooked up here ended up being basically that the device tells the host, hello, I am an audio device. Please send analog audio over the data pins. So that's what happened over there. So after that, I guess people have learned a little bit more about how CC pins work, because the specification is kind of funky in that regard. It's USB-C is not trivial, and this is definitely not a call out as in haha, look how stupid they are, because it is tricky. And I've also struggled a little bit with it myself. Reading the specification, it's not trivial. But after this, it got quite a lot of publicity, so that people were aware of the issue. So I guess that's the good side with it. People could learn from that mistake. So going back again to the chat. Yes, exactly. Great work, by the way. Please keep it up. Thank you. So now I am in sync with the chat. No backlog. Back to the Game Boy. So let's see again what changed here. So instead of having these as dynamic memory with malloc, they are being allocated as static sections and emulator data. Perfect. And yeah, I have a vague memory of writing this code, but I don't know. Is little endian, that make flag is, or that definition is very important, and it is defined. Good. Perfect. Then we can add that. Nice. Shared. We added some stuff. ESP utter is gone, which makes sense because we don't have that file. Oh, again, this is SMS plus. Oh, right. I should read better. I'm actually bad at reading, it seems. So we can throw away actually all of those files, because SMS plus Go is my early attempt at porting the Sega stuff, and we don't want to spend time on that. So I'm gonna revert all of this. Discard. Yeah, let's burn it. And again, let's just double check that we can in fact still build the NES stuff. Yep, it still builds. Good. Okay. Cool. Let me move on. So let's build the Game Boy stuff. Okay. Undefined reference to ROM data. Let me check in the reference project because I have probably just forgotten to add a file or something. So if I search for this, we have GB-ROM. And then we have ROM info somewhere. Okay, core inc. Alright, so the script that I adapted should actually have this stuff in it as well. So let's fix that. That's only part of the issue. Okay. So actually, this should be like this, and this should be like that. Alright, I need to do. Hey, look at that! It links. It links. So here comes the. This is a little bit scary. Now we can actually try it on hardware. So, okay, I'm just gonna read the chat before I continue. I'm not good with soldering, so if I will be following along the connections mentioned, will it be safe not to break the device? I mean, if I shorted 2 pins or so when I hook. First of all, if you're using hooks like clip-ons or whatever it's called, always like if you're no exactly we can never give guarantees on this. That is correct. But like if you're unsure about what you're doing, always disconnect power, because if there is no power, then if you short something, it will probably not break. There could still be some capacitance somewhere, so it's not a guarantee, but it will definitely be less likely that you break something. And like stacksmashing is saying, yeah, we cannot guarantee anything. Never, actually, with anything of this. It could be that this method actually leaves a trace of something that will break later. We don't know, and we cannot guarantee anything. We just share what we have done because it's nice. But you are 100% on your own when doing anything of this, just so you know. Okay, so I think now it's time to flash. Oh, why doesn't it? So I have this ZSH is usually good at coming up with suggestions, but in this case it didn't work. And you will void warranty too. Yeah, of course. I mean that that is given. But sure, of course you need to know about that. Cool. Let's go. So here is the old NES ROMs running, and here we are flashing the Game Boy emulator to the external flash. Which takes a while, of course. Okay, it's done. So now we flash to the internal memory. So let me bring up the big screen. Okay, so this does not look very good. We have to do it one more time. Yeah, it would be nice to improve the stability so that you don't need to like do things multiple times. But yeah, it seems that it's breaking early. Quite Yeah, that's correct. Oh my ZSH. I like that. But it's often very smart and you get used to it. So when it is not smart, you get, or I get a little bit like, what? But it works so well otherwise. Why isn't it working now? Because I think, now that I think about it, it's probably because I'm using a custom make file. Because if I just do like make, okay, it won't work in this project, but like in other make projects where you have a file called makefile, it will parse that makefile for you and come up with make targets. Yeah, so I don't know, it broke. Anyway, now the fun. Sometimes it's too smart. Yes, you are correct. Like, have you tried like r-syncing files? You have tab completions on your remote server and stuff like that. It's kind of far out. I like it, but yeah, it can be a little bit too smart. Okay. So let's do like that. And then, wait a minute. Why didn't it? All right, I should do like that. Oh. Okay, so let's set a breakpoint. Or actually, let's just continue. And okay, so we are actually in an error handler in main.c, line 187. So okay, this is actually, this shows up when the flash driver is borked. Why would it be that? It worked so well before. So didn't I just rename it? So as you can see, it's just 888888888, which is not correct. So just to be sure, I'm gonna flash the NES emulator project, and which will obviously not work, but it will at least initialize the flash in the same way, and then we can debug that. And we can, okay, we can see that, okay, it is actually borked. Why the heck is it borked? That is weird, because wasn't I running the NES emulator just now? Let's do that one more time. So what I'm doing now is, I've probably messed something up. I just want to double check that my baseline is working. So I'm using the same project structure, and I am asking for the NES emulator to be flashed onto the external memory. And then I will flash the internal memory, and basically if it works, okay, it doesn't work. So I have messed it up. So now it's time for the dreaded debugging session again. What the heck? It was working so well just now. Very annoying. And honestly, I don't understand. So did I change anything? Main file is completely unchanged. So actually, what I'm gonna do now is I'm going to remove a few files. This one. And let's just revert that. Take this one and basically replace it like that. Will commands differ if using JLink than SDLink? Just a slightly bit. So actually, in this project, I haven't cared about anyone else. I only care about myself right now for the time being. But with the backup project, yes, definitely it is supported. So you just pass a different argument. Let me show you. So when you run the script, you run, yeah, it is the first argument. So I can show you like this instead. So for example, if you want to run the restore script, it tells you you have to pass jlink or stlink. So in your case, you just run it like this. And in my case, I run it like this. Okay, so what I'm doing right now is I'm gonna clean this project up so I can commit it, which will enable me to diff and go back and forth between branches, which is nice. So yep, there we go. Main NES. Yeah, right, I had to rename that. Game Boy input. Right. So I'm worried if I messed something up in this rename, so we'll check that in a minute. So I'm just gonna add all of these changes, and let's just call it GB. And right, and then I need to go into the submodule and do like this. And yeah, it's just a tiny. All right, these changes are kind of interesting. Yeah, we definitely need those. So let's just do like this. So now that is fixed. Now we have a commit in the submodule, and which means that we can also add that to the change list. And now we can commit all of these changes and call this Game Boy work in progress. So now that is stored. So now we can go back to the main and build it. Wait, did it fail? Oh yeah, of course. And it links, yep. And then let's flash it to the external memory. And hopefully this will work. And then we can diff the files and figure out what I broke. Because obviously something is wrong. Okay, this makes me sad and worried. This indicates that something is wrong, either with my hardware or something else. So this is not good. So I'm gonna change to SPI mode because that worked better. Okay. Oh, hard fault handler. Why? Okay, I probably need to flash the external memory as well. So the thing is, I just naively thought that changing this would just be a change without any difference in the size of the binary. So the thing is, when you have code, and yeah, essentially when you have a separated external flash memory, you always need to keep the internal and external flash memory in sync. And the way you should do it is to always flash the external first and then the internal. But I just skipped ahead and programmed the internal flash. Okay, but this is... what the heck? Okay. I don't know what's going on. So I honestly don't think that the changes in RetroGo would affect anything, but let's just be sure. So I'm just going to go into the submodule and check out the original branch, the old branch that I know works. And then let's build. Okay, it's loading. Is there a firmware dump unique per device or same for any device? I mean, if you have yeah, so to answer that question, I can tell you that it's mostly the same. So the external flash is identical up to a certain point. So there are 2 pages in the end that are different and unique per device, even if they are from the same country. And then the internal flash seems to be 100% identical, if I'm not mistaken. Because what we do here in the backup project, we have a hash of the internal flash backup, and then when we actually do that internal flash backup, we dump the whole thing, and then we check it. I think. Let me just double check that, just so I don't. Right. Yeah, exactly. Yeah, so this confirms it. So what we do here, so the thing is that stacksmashing and I, we haven't done everything together. He wrote this script, and I'm reading it like just now for the first time. But essentially what this does, it dumps the internal flash into a file, and yes, it dumps the whole 128 kilobytes, and then we do a checksum or a hash of the whole file. But for the the external flash, we cannot take a hash of the whole flash because it is different. So what we do there is we do this instead. We dd and copy only up to a certain point. So there are 8 kilobytes in the end that differ. Actually, it's not fully 8 kilobytes, but it's a section of 8 kilobytes that contain unique changes. So to answer your question, yes, the internal flash is indeed 100% identical. The external flash differs, and there are up to 8. There are the 8 kilobytes in the end that differ. But I have actually taken the external flash from one device and put it onto a different device, and that worked with the stock firmware. So even if these pages in the end are different, they can still be. It can still work. And I guess the theory is that they contain localization information, for example, which language and stuff. Okay, yes, at some point we'll have to provide some solution for WinMac users. Yeah, definitely. Someone made a pull request which adds OpenOCD for Windows and some scripts, which is nice. But I think we need to rework this a little bit because yeah, we can't really have OpenOCD checked in the same repository. But this is really nice to have some people from the community to contribute. So that's really cool. We just need to sort of clean it up a little bit. So here, yeah. Yeah, the thing is, again, the OpenOCD version that you can install on Ubuntu is too old. You need a Git version. It's sadly like that. So it means if I brick a device, I can restore another device. Yeah, correct. But still, I don't want to give any guarantees. But Yes, I have done it, and you probably can do that too. Okay, moving on. Let's flash the internal flash. Okay, it's borked. I don't understand what the heck is going on with my device, because obviously it worked before you saw it all. So maybe it's my wires that are spooky. I honestly don't know. Um, yeah, we can provide a static Linux version. Yeah, we can. I was thinking of setting up a Docker that builds OpenOCD from Git and publishes an artifact, just so that people can see, okay, it's built like this, and here's the artifact. Fine, because publishing a binary and telling people, here, run this compiled binary. I don't like to do that, and I guess other people don't either. So just having some sort of reproducible build that is built automatically on a build bot, that is the way to go. Okay, so I'm gonna use this one, flash loader. Yeah. So sorry for the chaos. I just like to keep projects on different desktops, because having everything on the same editor can be extremely confusing. So I'm just gonna open up the chat in this desktop as well, and do like this. And we are back in business. So first of all, I'm gonna set this to 0. So what I'm doing now is that I'm using the flash loader project in order to debug what the heck is going on with my device, because something is not working. Right. So actually, I haven't reviewed what happened here the last few days. I need to pull. Thanks for the follow. Right. Okay. I saw a video from a guy preparing a place, adding a micro SD slot, as he hoping it might reach to that level at some point. Will this might be possible in future, theoretically? Well, as I said before, you could most likely connect a micro SD card to the flash I/O pins. However, you probably cannot use the OctoSpy peripheral to get memory mapped I/O. However, if you are okay with some latency, for example, if you load a chunk of memory into RAM and then execute that, if you're okay with that, then yes, you can most likely write a loader so that you have like a 1 terabyte micro SD card with every single game on the planet, and then you can mem copy that into RAM and work on that. That is probably possible. You will of course consume RAM for the memory that you need. Like I shouldn't say no, it is not possible, but I will also say, well, it requires more work, and it might be that the end result is not great, but I will not say no. So in the meantime, we are working with a 16 megabyte flash memory instead, because that gives us a lot of storage and allows us to still keep using the OctoSpy peripheral with the memory mapped I/O and all of that. So I think that is going to be nice. I mean, 16 megabyte is still a lot of memory. Like even if a ROM is like 500 kilobytes, like a very huge ROM, yeah, that's a lot. So is 16 max? Yeah, that's a good question. And honestly, last time I checked, that was the biggest one I could find. But we can Google a little bit. So this is the chip that I'm using. So let's just see if there is a 256 version of that chip. Doesn't really seem that way, but or maybe. Okay, it has a different package. Okay, with, oh wait, that's a D. Is that 3.3? No, that's 1.8. Okay, so with some creative soldering, you can most likely solder this. Then you get 32 megabytes. Because this is a different footprint. It is not the other one. What's it called? SOP. I always mix them up. Soik, right. So Soik, this is the one we're using. Yeah. And the other one is a WSON, which is, as you can see, surface-mounted legless, whatever it's called, leadless, leadless package. So there are no pins sticking out. Yeah, it is what it is. Here you have the one we have. Oh, yeah, you definitely need to be creative in your soldering, because this is actually quite a lot bigger, wider, as you can see, side by side. If yeah, honestly, I don't know. I shouldn't say anything actually, because what you should do is you should look at the datasheet and look at the size. But definitely, it's not impossible to use a bigger chip, but it will require some hacky soldering. I mean, you could also do like an adapter board for it, but at that point, I would say you can probably do it in a nicer way with a different chip, I guess. So that's the biggest that I've seen that fits. 1.8 volt and package wise. Yeah, exactly. There are larger chips, but it seems that 16 megabyte is max for SO8 and is using larger with will you consume more battery. So actually, I don't know, but probably not by any significance. The flash is usually very power, like, what's it called? It's not power hungry. We can actually check what the power consumption is, but the LCD will consume way more, I'm sure. So we can actually check it up. So if we go to the PDF, yeah, it probably says here 7.5 milliamp. Whoa, that's actually a lot. Huh. I stand corrected. I actually, I don't know why, but I assumed that flash memory was not that expensive. 7.5 milliamp. That is a lot. But in the big picture, it's not a huge amount. Like Tim made some power measurements, and if I remember correctly, it was in the ballpark of between 50 and 100 milliamps. Yeah, let's see here. So if you play music at maximum volume and have the LCD at maximum brightness, it consumes 100 milliamps. And at the lowest setting, it consumes 28 milliamps, which is, yeah. So 7 milliamps is significant, definitely. But yeah, if using a bigger one uses more than this, I don't know. So maybe the 7.5. Actually, we can check that. So this is the stock flash. Um, uh, this one, I think. VSSA read. Yeah, okay. So at high speed, it consumes 6.7 up to 8. So I guess it depends on how you have configured the. All right, here we have 2 IOs. Here we have 4 IOs. Actually, 9.5 is okay. So if we use it at the quad in quad mode, it uses actually 9.5 milliamps. But this is the flash that ships with the device. So I honestly I don't know if there is any correlation between size of the flash and power consumption, but I learned something today. I did not know that flash was this power hungry. Like 10 milliamps. That's a lot. Wow. Um, yeah. Okay, come on. We're not reading it constantly. 10 microamp is fine. Well, you're right. We're definitely not reading it constantly, for sure. But it's still like surprising. I didn't know it was that expensive. But yeah, it's obviously just when you're reading it. No, that's not obvious, but that is how it is. So I guess actually between between reads, you could actually power it down into deep sleep, where it only consumes like almost nothing, 40 microamps. That's not much. But yeah, this is 10 milliamps, not microamps, so it's a lot. Those are max figures. Typical is lower. Yeah, okay, sure, 6.5, but it's still significant, I would say. Anyway, moving on. Let's debug my crap. So, what is the exact model recommend one to use for now? So, I cannot recommend anything right now, but I have bought this chip and I have made that work. That's all I can say, really. And as I said before, this chip is not compatible with the stock firmware. So if you go with this chip, you have to use homebrew. That is how it is. Maybe we can patch the original firmware, but that is not something I will do. Maybe someone else want to do it. Yeah. So anyway, yeah, this chip, sure, you can buy it, but I cannot say that yes, I recommend this. This is the one. I just have it. That's it. Okay. Going back here. Right. So, right, we wanted to look at the changes. So what has happened here? So, run from RAM. So maybe there is some issue with this. I don't know. So we added a read command. That's nice. So this will read without the memory mapped mode. The reason why we need this is because when using the ST-Link and when you're in a hard fault, you cannot use interrupts in RDP level 1. So before we wanted to use the memory map mode, but for some reason it didn't work reliably with the ST-Link. So we settled with this solution instead, where we take we send basically a manual command to the flash chip to read out those bytes that we want to read instead of using the memory map mode. So that's what this does. Okay, and here's the linker script changes, where it relocates stuff from flash to DTC RAM. And that's pretty much it. And then this stuff is a little bit... Oh, this is actually important. So it does not do reset halt. Because when you're in RDP1 and using ST-Link, you cannot do reset halt. At least we were not able to do that. Maybe it's possible with some configuration, but I have not managed. So let's first of all go to the main function, yep, and disable the writing, and then we will make clean, and then we will make flash. What does make flash do? Let's check it. Oh, it actually doesn't do anything. Right, because we make it and then we use OpenOCD to load it into RAM and execute it. That's how it works. Until the stock firmware is not disassembled and analyzed thoroughly, I'd refrain from changing flash if you're planning on running stock firmware. Yeah, I agree on that. So if you want to run the stock firmware, don't change the flash at all. At least not yet. 1 megabyte is still a lot. As you will see later on when we get Game Boy running, you will see that we can in fact do quite cool stuff, even with only 1 megabyte. Okay. Where do we have the files? So what does the script do? Just a recap. So this script, flash.sh, in the flash loader repository, what does it do? It prepares arguments. So the binary we want to flash, where we want to flash it to, how big it is, and if you want to erase the page. And here are some helper functions to get the addresses of various symbols, and then we prepare it. So reset halt, and then it will load, instead of programming the flash, it will load the ELF file into RAM. It will reset the device again, we'll sleep a little bit, and then it loads the image you want to flash, and then it sets the variables, and then it executes from aux20, which, if we look here, is this memory region, DTC RAM. And as you can see here, we are putting the ISR, LCD, text, read-only data, the ARM stuff, pre-init stuff, data, everything goes into DTC RAM. The reason for this is so that we get a RAM located image that we can then execute. We upload it to the RAM and then we execute it. So what this does is it prepares the stack pointer and program counter. That is what it does. So let's run it then. So let's run it using flash. Actually, I'm gonna change this, yeah, and then I will do like that. Has this, I need to read the script a little bit better. Adapter config.cfg, right. So here you can select which adapter you're using, right. So in my case, I want to use ST-Link. And it still breaks. All right. So in the ST-Link configuration, you need HLA SWD. Okay, stuff is happening. It crashed immediately. I honestly, let me just double check. It almost feels like I'm having a connection issue with the SWD programmer probe. One more time. This doesn't work at all. Why is it so sad? So I'm able to run reset halt. Oh, right. I forgot to add reset config none. So we should definitely split this up so we have separate files for the separate programmers. So the reason why it didn't work just now is because this important line was not included here. And actually, it should be before init. Yeah, so you set the reset config, init, and then you do reset halt. So you can actually do it like that. Okay, one more time. Okay, this looks better. Much better. Oops. Okay, starting flash process. Right, 1 megabyte is, it takes quite a long while to program a full megabyte. But shouldn't really take this long. Let's check the script. Right, so what it does now, the script, is that it's in this loop where it checks for the done magic, which is a special word we write when we're done. I don't like this. It takes too long time. It shouldn't be this slow. I'm just gonna... Oh. Yeah, exactly. So let's debug it. Okay, I don't like this at all. SPI mode, yeah, sure. But why am I executing from Flash? It seems that it's using the interrupt table from the old project. So maybe I got a hard fault. Because why is my program counter 0x08? If something went wrong in this, all of this program is located in DTC RAM. So I'm guessing I got a hard fault for some reason. And because if I think this is the program that is stored on the flash. So I'm back at the RetroGo stuff. And if I debug with this one instead, I am in the reset handler. Okay, interesting. Let's go back again. And run the script. So again, just so we go through what it does. Wait, did I change anything here? Oh, I didn't save. What? This... What the heck happened here? Okay. Okay, so I haven't made any changes to this script. yeah, it's supposed to. You know what? I'm gonna do something here. I'm gonna comment this out and just to exit. I'm gonna leave the, yeah, I'm gonna put the exit here. So what this means is that when I run the script, I will load everything, and then in the final step, it will keep the debugger open. So I can actually do like this. Like so, just so I don't miss it. So let's do that. So what I'm debugging here is that my theory is that I have this project stored on Flash. When the microcontroller boots, it will load this project's interrupt table, and then when I load this into RAM and execute and get a hard fault, then for some reason I end up in the Flash. Okay, attach debugger now. Let's do it again. Why am I here? Oh, right. Okay, so I take back what I said before because I just realized that if I look at this, I'm actually in the reset handler. The reset handler is the entry point of the program that is stored in Flash, and that is fine. So let's resume. So this address is just the reset handler of the old project. So when I press oh, actually, I'm gonna set a break in main, which is stored in RAM. You see OX2 0. So when I press continue here, I expect no, this will not work. Sorry. I need to do this. So when I type mon, it's a short for monitor. It will pass whatever I write to OpenOCD. So let's do that. So now I have changed the stack pointer to whatever is stored in this memory region. And here we can actually see that this is funky. This is not correct. Why is the stack pointer using 0? That is ITC memory. So here's something funky. This is not right. And then set PC. It will move the program counter to whatever is stored in Flash or in the RAM that we just prepared. And look at that. Those pointers are messed up. So what I think is happening here is that the linker script is a little bit wonky. So the ITC RAM is not being used for anything. However, we are locating stuff there. So this is very strange. I don't understand. How can it be so broken? I mean, it worked before. Very strange. So if we instead, for example, no, I'm not gonna do this manually. That's just stupid. So what we can do is we use arm readelf. I usually do that. Then we can look at the elf file. I'm gonna pipe that to like so. There we go. Then we can look at this together. So what readelf does, it will take the elf file, the binary with sections, and it will print all of the information it contains. So now we can actually look and try to understand what happened and why. So here, already here, we can see there are some sections at 0, which is strange. crt stuff.c. that sounds strange. What? Okay, where did that come from? Did I clean? Okay, it's identical. Okay, let's see if we can find anything more. Okay, so what the heck? So main.c is located in okay, so maybe for files. So honestly, I don't know the output of readelf that well. I've only used it a little bit. But we can see here when it's a section, the pointer seems to be actually, or the value seems to be an actual address. And when it's a file, maybe the value is not anything that we should care about. Okay, fine. So what I'm looking for is basically, do we have any addresses at 0? Has something by accident been located at 0 for some reason? That is what I'm looking for. But it seems actually here. Okay, so this is kind of interesting. So this indicates that the symbol min stack size, which we have here, is supposed to be in DTC RAM. However, the value. No, okay. Sorry, I take that back again. So min stack size is a value that is actually this value, right? So that is actually correct. I was worried that that it was located at that offset. Okay, let's continue. Okay, so this actually looks pretty good. So what I'm trying to figure out, just in case it wasn't clear, why was my program counter and stack pointer that I dumped from the newly updated RAM, why was that so funky? These values. So what I'm looking for is basically what we are storing here. Why are we storing an incorrect value in that address? So let's see if we can find out. So I was hoping that readelf would tell me where that value come from, but I guess it's not that simple. So I have to look at the DTC RAM that is stored here, ISR vector. So this is the entry point. So if we look at that, yeah. Right. Stack. Exactly. Reset handler. Right. Okay. So now it starts to make sense to my head. So what you're looking at here is the so-called startup script, which is an assembly file, which defines the section called ISR vector. ISR stands for interrupt service routine, I'm pretty sure. And it is the very entry point. This is where everything begins. So the first value, the first word that is stored, with other words, this one, contains this value. Where does that come from? It is the thing called E stack. It's where the stack ends. Where does the stack end? Well, here we define it to be this value, end of RAM. However, when we read it, it is this. So let's go back to this project, the previous one, and let's debug it. So again, here we have the reset handler, and we have the E stack. So let's read the words at oh, now I read a little bit too much. And here we actually see those two values. Okay, so I'm starting to think that the ROM has not been loaded, or the ELF file has not in fact been loaded. Because we can double check this, we can do the following. We can do xxd and look at, so xxd-g4-e tells the hex dumper to show 4 bytes in a group and to endian swap them so that we're looking in little endian. Then we will look at the build artifact and we will look at the bin file. And this looks nice. So what this tells us is this is the actual binary. The actual binary that is supposed to be loaded into DTC RAM. And the first word is the ISR vector. The first words, this is the ISR vector. Here's also all the interrupt handlers. So if we look at the assembly file, we can see here we have the eStack and reset handler. So if we, in this console, just to make it easier to visualize, I'm just gonna do like this, and we can dump, we can do like that actually. So this is supposed to be eStack, right? Okay, GDB couldn't identify a symbol for that. However, this one then, that is the reset handler. Okay, so what have we just done? We have looked at the binary with the hex editor. At offset 0 in the binary, we are expecting to see what is supposed to be loaded into DTC RAM. The first values are the ISR vector, which come from this file. So the first 2 values is the eStack and reset handler. This one looks definitely like the end of the stack, and this looks definitely like the address of the reset handler. However, when we look at the memory at OX, so what the flash script is doing is it's reading these words, and they contain the 2 values from the flash. So this proves that we have not loaded the binary. So let's do that. Let's see why this isn't working. So now I have a debugger running again, and I will open up no, I will open up GDB non-reset halt. So again, now we are in the reset handler, right? Yeah, again. So this is the reset handler of the program that's loaded in Flash. So essentially, we are here in the script. So now we need to program the ELF file. And I'm starting to worry that this doesn't in fact work. So just to look at some values, let's look at the most important values, these 2. So these 2 values contain the values that come from the flash. Okay, let's load I need more consoles. So we're gonna load this. Oh. All right, one. Okay, so OpenOCD claims that yes, I have loaded it. I think I start to see the problem now. But anyway, let's check it out. This looks nice. Fine, okay, so, and then we do a reset halt, okay. And now it's reset. Okay, now we have actually found the cause. So in case you didn't see what just happened, is that I was debugging the script where we reset the processor, we load the flash loader, and then we call reset halt. But what this does is that it will reset the memory over here. So we should in fact not do this. And instead we should just continue. So that must be the bug. I think we found it. So let's run the script. Oh, actually, yeah, we can let it run like this. So now we're running the script, but this time without the reset halt at this point. And then after we have loaded the flash image that we want to program into RAM and updated all of these values, we will attach a debugger. So we are now at this point in the script. Cool. So now we do make debug. And again, we are at the entry point of the other program. No, wait a minute. This is not right. Oh, sorry. This is right. So now we're just going to do these two manual steps. Boom. Yeah, this looks good. And this looks good. And when I press continue now, actually I can just do like this. What the heck? Okay, I'm confused. So what just happened? I told OpenOCD to read the memory at this address and store that value in the program counter. However, when I print the program counter from GDB, I get a completely different value. Why? It doesn't update. If I step one instruction. Okay, now it updated. So it seems that GDB had sort of cached the program counter. So don't think too much about that. Let's press continue and see what happens. Yep, okay, so it blinks fast, which means that I hit the hard fault. 193, okay. Oh. Oh, okay. This is interesting. So it didn't actually, but it can't be this fast. The delay seems very off, but they are supposed to be implemented like this. Right, perhaps I need to update this to the 280 megahertz clock. Because in this project, it gets complicated. Okay, anyway, everything seems fine. But this is not fine. Alright, I have no idea what's going on. This has been very frustrating. You know what I'm gonna do? I'm gonna revert, or stash, and I'm gonna check out the previous commit. And I will try this and see if it still works. Tangle wires coming loose. Yeah, you know, I am starting to worry about that. It could definitely be that. Could definitely be that. And if it turns out to be that, then I'm sorry I have wasted all of your time and my own, which sucks. Okay, let's flash. Oh, right. I need to stash pop. Yeah. And we can revert. I just want go away. Okay, cool. Let's okay. That's good. Let's run the Flash script. So now the code has been reverted back to the old solution where we are programming the device and storing the Flash loader program onto the Flash instead of executing it from RAM. Because obviously there are some issues when executing from RAM, or I'm having hardware issues based on my soldering, which is not unreasonable. Okay, this looks good. Let's check it out with the debugger. Okay, I think I need to solder. I believe my device is simply borked. So yeah. So that means that the last hour or so has been sort of a waste. So I will go to my lab and solder this. I will end the stream soon. But anyway, I'm just gonna check the chat. What would be the Mac OS command equivalent to the Ubuntu one, as I can't find any of the formulas on Brew? OpenOCD should be there. Yes, definitely. And actually, stacksmashing, he is running Mac. So I haven't tried it personally on Mac, but really, it should only be OpenOCD that is, or actually, yeah, because you don't need to compile the exploit. In the repository, yeah, right. Brew install OpenOCD. Yeah, perfect. So I don't know really how you install the ARM toolchain, but you don't really need that for the for the backup tool to work. But it's there as well. Okay, perfect. Nice. Yeah. Okay. So this really makes me sad because I I damn it, I really hoped that my wires would survive for a little bit longer. But we can try one last thing before I give up. Just gonna lower the prescaler, and I'm gonna change the SPI mode to SPI mode. All right. Let's see what happens. Okay. Look at this. It actually erased, but it didn't program. You know what? There has been too many of these sort of unexplainable problems. So I'm gonna say, yeah, this is probably the flash, I guess. Or I mean the soldering of the flash, which is really a shame because it's been so convenient to have it like this. I mean, okay, I'm gonna do one last try. One last thing. I'm just gonna memset with, oops, like this. I just want to confirm this. Yeah, and then I can remove this. So what this does, it does a chip erase. Oh, this is not good. Why does it break? So it hits the error handler of the program. Why would it do that? So it means that this failed for some reason. We can check the state. This is not gonna work. We're gonna need the correct pointer. Okay, it's 512. What does that mean? 512, also known as OX200. Okay, it's a generic error. Well, that's great. Why? Okay, so timeout. Maybe it hit the timeout. Okay, you know what? I'm gonna accept defeat and say that okay, I blame my soldering. That has to be it. Okay, so let's wrap this up. I will solder. I will end the stream and solder the flash so that it's 100% nicely soldered, and then I will try to wrap things up with the Game Boy merge. And when I get that running, I will commit the code and post it on Twitter. So please keep an eye out for that. And thanks again for joining, everyone. It's been nice, and there's been some really nice ideas about the modding, like ways to mod it. So I hope to maybe do a stream later on where we can explore hardware mods more thoroughly, and perhaps come up with some cool creative ideas and maybe design the PCB together, because that's always fun. I want to do some more hardware streams as well. Maybe we can, when I get the parts, maybe I can stream the soldering and bring up of that. That could be pretty interesting. So yeah, look, let's hope we can do that. And thanks again, everyone, for joining. So yeah, bye.